Okay, in this video I'm going to talk about the wave equations. So let's go directly and understand more about it. First of all, if we're going to look, for example, to a rope, a flexible rope, as you can see here, and attaching it to fixed end to a wall, for example, and from the other end we are holding it firmly, and then we started to vibrate this rope, bringing our hand up and down, or making our hand to induce some vibration in this rope. We're going to find that this rope is going to take different shapes at different times. So this is the important part here, that it is going to have different shapes at different times. Means that at every particular time, or at every specific time, there is, for example, at T1, there is a corresponding shape for the rope. For example, if we are going to have this example here, which is this rope, as you can see here, it is in blue. If we say that we are going to have the first wave, look to this first wave, for example, here, this first wave, that you're going to find that the rope is moving as you can see here. This is the shape of the rope when we are moving our hands, for example, up and down the first time. After that, we are going to find that if we're going to move it again, we're going to find that the second wave is going to be formed in this dotted line, for example. And the third wave, then we are going to find that there is a third wave that might also form, and the position or the shape of the rope is going to be different than the previous one. So the point here is that at every point of the rope, this point, it might go up and down, and in the same time, let's clean everything, this point may go up and down, and in the same time the shape of the rope is going to be changing, right? It is different, right? So this means what we want, a kind of a function that is going to describe this this rope, or this rope position at any time. This is what we want to have. So if we have vibrations in a membrane or steel plate, if we have a steel plate, or oscillations along a guitar string, for example, or are all modeled by the wave equation. This is the importance of wave equation here, that it is going to give us the position of any point along the rope at any time, and appropriate initial and boundary conditions. If we have some initial and boundary conditions, then we can put an equation. We call this equation wave equation. Okay, and suppose an elastic string has its ends fastened. The string is displaced, released, and allowed to vibrate in a plane, which is this plane, for example. If we have this is X and this is Y, for example. Or if you have if you are lying by the beach, for example, or something, and you are going to find some waves are approaching you, you're going to find the waves are changed with time. They are not fixed, right? So that's what we want to describe by a mathematical model. Okay, so now we are going to have it like this. So if we're going to place the string along the x-axis, this is x-axis, for example, here, and from 0 to L, that assume that we are talking about some infinite or some finite or some length for the rope that we are talking about, and assume that it vibrates in XY plane. So this is the XY plane. The rope is going to vibrate in XY plane. So we want a function, take care of this, we want a function which is exactly, now we started to say y x of t. So this x is what? It is the horizontal axis independent parameter. But we have another parameter here, which is exactly, it is the time. The time at which the profile of the wire or the rope is going to take a specific or a particular shape. Okay, so the function that we are searching for, it is going to relate like two independent variables with one dependent variable, which is y. So we want to know this point, for example, at a particular time, t, and with independent variable x, for example, this is going to be x here, okay, x1 for example, then where is this point will be along the y-axis? It will be here, or here, or here, or here, or here. We don't know. So we have this vertical axis is going to be our dependent variable, and we are going to say that the position along x and the timing is going to be the independent variable. Okay, so these are the equations. So the function is going to be y of x and t such that at time t, the graph of this function is the shape of the string. That's right. So it is going to give us the shape that we want. It is going to be something like this. Okay, the shape of the string at that time. Okay, so this is maybe at t1 for example, but the shape in the t2 will be like this. At t3 it will be something like this. At t4 maybe it will be something like this. Okay, we do not know how it will be at every t. So if you are going to look to the point, this is point x for example, here, here, here. Okay, so this is like the same point. If we say that this is the same point going up and down in terms of y, so this point at x1, let's assume it is at t1, it was here giving us, let's assume y1. At t2 it was giving us y2. At t3 it is giving us y3, and so on and so forth. So this is the meaning of the graph that we are talking about. The shape of the string at that time. We call y of x and t the position function. We call it the position. Now we could understand what is the meaning of position, okay? For this string. Okay. Now we want to put this in a mathematical form so that we can understand it, and we want to derive it. So we are going to derive from the first principles, starting from a position x here. This point, it is going to be like represented. Okay, this point, if we say that it's the xy plane, it is going to be represented by x and t, and after a while it is going to be, or after certain distance here, which is x plus delta x, it's going to give us another position for the same point, okay, which is going to be x plus delta x and t. So the movement from here to here is going to have some change in what we call it the tangent here, which is theta here, right? So theta here is going to be like theta, for example. This is the tangent here, and theta here, it is going to be theta plus delta theta, right? Okay, based on this and these relations, okay, we are going to describe the y, which is the position function, which is y of x and t, at fixed time. So this is going to be at fixed time. This is the position or the shape of the wave at a fixed time, at specific time. Mathematically, and using our mathematical skills, we can end up with an equation that is relating these three together, y, x, and t together. Okay, we found this. We found that if we're talking about one-dimensional wave equation, one dimension means that if we go back here, this is one-dimensional because we are only talking about xy plane. But sometimes we have like two-dimensional, something like this, for example. So we have xy in the plane and we have z here. So this means that if we have a wave in this in the space here, we are going to have like two projections, or we can say that there is one wave is going to be along x, another wave along y, and we are going to represent this space wave in terms of a function which we are going to call it z of y, and another function that is going to be in terms of x, which is z of x, for example. So this is what we call it two-dimensional, but we are starting with the simplest case, which is one dimension. So we understand now what is the meaning of one dimensional wave equation, as we said. Okay, we found that very nice equation after some derivations, simple derivations, we can obtain this, which is, we found that partial squared y over partial t squared equal to c squared partial squared y over partial squared x. What is the meaning of this? First of all, this meaning partial, what is the meaning of partial? It is like we are, if we have like y, x, and t, so we have like multiple variables here, right? Multiple independent variables. So we are going to deal, for example, with this x as a fixed term, and we are going to say this is our main variable. So we're going to say this is like partial y, partial t, okay? So this is the meaning of partial. This means that derivation of a specific of a function with respect to a specific variable. In this case, it is t. So here, the left-hand side is giving us the second derivative of y with respect to time. Can you imagine this? Try to keep this in your mind and put it like this. We have like, for example, partial squared y, partial t squared. This point is, we are describing it, remember that we have y-axis here, we have x-axis here, right? So remember that this point is, or we can say this term is representing this point at what? Exactly, it just gives us what this point like at fixed x, if we say x1, because we said that it is the partial here. At a specific point along x-axis, let's assume it x, this point is going up and down, okay? And this point is going up and down with what? Exactly, with a kind of acceleration, right? Because partial y, partial t, it is the velocity of the point up and down, and then partial squared y, partial t squared, it is what? Exactly, the acceleration. So we're talking about the acceleration of the point, the vertical acceleration of them in the same point. I'm talking here about the same point going up and down. Okay, let's clean. Okay, so this is the left hand side, which is, I can call it clearly, the vertical acceleration of the point. So if the wave is going like up and down like this is at point, let's assume it is going like this at this point x1, found that this spike here, or this the maximum point here is going, maybe it is going to be something like this going down, or maybe going like something like this going up. So the point itself is going up or going down at the same position. So this is what we call it, the vertical acceleration of the point. We found that after the derivation, I said that after the derivation, after the simple mathematical derivations, you can find it easily in the textbook. It's not our concern actually. And we found that this vertical acceleration is going to be related to partial squared y over partial x squared. This is what? Exactly, it is the horizontal acceleration. So this means that this point is going to, if we're talking about the horizontal axis, this point, as if the wave, if we say that this is the wave, you're going to find that this wave is propagating, like as if that it propagates with acceleration. This is what we call it, the horizontal acceleration. How much it how fast this propagation is. It's the acceleration, okay? It's not only the velocity, it's the second derivative. It is the second derivative. Look here, for example, I'm going to say this is one wave. Take care of the time that I'm taking for drawing. There is another wave, for example, like this. Which one is faster? The second one. And the second one, I put it with some acceleration. There is change in the velocity, change in the speed. So this means that the second wave is like having more acceleration than the first one. So this is what we call it, the acceleration, horizontal acceleration. Well, and what is this? It's a constant. C squared, it is a constant. So this means at the end that the vertical acceleration at any position x1 equals to the horizontal acceleration or propagation of this wave, and they are linked with something called c squared. It's constant, something constant related to the density of the rope and so on. That's it. This is what I want you to keep in your mind whenever that you are being asked about one-dimensional wave equation. Okay? Okay. So now let's go to the next part, which is if we have the wave equation in two space dimension, how we are going to use it or how we are going to solve it. As I said before, space means that, or two-dimensional means that we have x, y, and z. And this means that if we have a space wave, as you can see here, we are going to represent the space wave with exactly the yellow waves that I have drawn here along y-axis and along x-axis only, which is going to be with respect to, as if that we are going to talk about this, like partial squared z, partial x squared, sorry, this is y squared here, because this is along y, and here we are going to use partial squared z over partial x squared here. And then the main function that I want to describe is what? Exactly, up and down, which is going to be partial squared z partial t squared, right? This is what I want. And actually this is how the equation is giving us. It gives us partial squared z over partial t squared equals to, so this is like the z with respect to t, okay? It is how this equation or this wave is going to be described, okay? Which is this one. It is going to be described by two terms. The first one, partial squared z partial x squared, which is exactly the x component, for example, of the wave, and another component which is exactly the y component, or we can say the acceleration of the wave along y z or in the yz plane. Okay, so this is how it works, and this is a constant. Again, this is a constant. Okay, and where that in which z x of y and t is the displacement function. Well, that's right. So we have here like three different independent variables, not only like two. Before we said that it was x and t because one dimensional, but if we are talking about two dimensional, we have x, y, and t, three independent variables. Okay, it is routine exercise in chain rule differentiation to convert this two-dimensional wave equation to polar coordinates. I think that you're familiar with polar coordinates in general, and instead of using xy Cartesian, we are going to use polar. We're going to use polar, which is r theta. Instead of x here and y, we're going to use r and theta, and we are going to describe the point as r and theta with respect of time. If we're going to make it, it's very easy to be obtained mathematically. We're going to end up with this, which is partial squared u partial t squared equal to a constant times exactly, we have some components here as you can see, so three terms here, partial squared u partial r squared, this is r as we said, this is the radius, okay, 1 over r partial u partial r, which is going to be like the derivation of u with respect to r, like as if it is like velocity along this radius or along this line, and 1 over r squared partial squared u partial theta squared, which is like the angular acceleration. Okay, these are like the representation of it. Okay, so we have now three different representation of the wave equation. Okay, one is the one-dimensional, another one which is the two-dimensional, third one is the polar coordinate representation. Okay, thank you and see you in the next video.